when I checked, before, like last week, I said, how is it? And when I checked 3, 4 of these engines that we developed over the years, and they all gravitated like that. The first time we went out with them, there were 10,000 lines, and after many years of use, they became 20,000 lines with all of the testing things and the additions and all that. How big that is? Well, 6 months, somebody can develop the 10,000 lines based on infrastructure we already have. It's not a lot if you know what you're doing, but it's very, very small compared with if your application really is 1 million lines of code, which is just like a medium one, right? So it's 2%. You have a big system. This thing is 2%. But it's the 2% that determines if it works, how good it is it correct completely, or you have problems. Now, if you are 99.9% correct, this is I learned that in Tavis group, you have no hope in the internet age. It'll work in every demo you want, but you have no hope in the internet age. If you only have like 1 million things, which is nothing in the internet age, you have 1,000 guys angry about it every day. You'll be out in 2 weeks. So if it works, and their use need to be 100% correct. Talking about teaching, this is what I try to teach how to build things like that. Up to a certain level I can. Beyond that, there's no way I can teach, at least not me. What I can do is I can expose, I can challenge, and I can mentor. And there's a big number of those that came through the lab went and built things like that, whether in the commercial world, in academic environments, and just have that capability to do it, and very few people can do it, unfortunately, and much smaller number of it can invent it. And that's what it's all about, in my opinion. So we're done 2003. First step is we're happy with it, and DARPA is out, by that time almost out, and we get a phone call. Phone call from Siemens to us on the line. We read your papers, we saw your code, we have a challenge for you. Voice over IP. We want to run voice over IP systems, and we cannot charge for them. Why? It doesn't get to the quality necessary to charge. What happens? For audio, there is a metric. It's called test. For a phone call, it needs to be a certain level to be relevant, to be good. And as the loss rate increases, on average, this is an average graph, the quality deteriorates. Once it crosses here, you're up. Once it crosses here, you cannot charge anymore. And that's an average. So there are 2 bad news items here. The first one, if you look at the blue line, it goes down. It's if the loss was uniform. But on the internet, it's not uniform. It's very bursty. It can be clean, then you lose it, then 70% you lose the next one. 66% you lose the next one, something like that. So actually, it's somewhere between the green and the orange. So that's what the real piece of bad news. It's not even the blue. It's here. And the second piece of bad news is don't look at average. Who cares about that? You need to look at the worst codes. They need to be good. And we looked at the worst 5th percentile. In retrospect of the years, that was not enough. You need to look at the 0.1%. Okay? But when you look here, once you reach 0.5%, you're done. Okay, if you want to look at the worst codes, 5%. So they say, oh, we read about your stuff. You have low average delay. We want to use it. Use it. It should work. 1 month, 2 months. Claudio, what's the problem? Tune it. Doesn't work. We can't make a dent. Just tune it like this and tune it like that. We are improving it by a little bit, but we're not improving it. There is something we don't understand. So that's where the interesting time of research starts, right? And then you come up and you say, okay, you need something completely different. You need a different protocol. We need to give up reliability. We need to be the best we can timeliness. And then we come up with something that the guy sitting here himself would say, don't say this word. Almost reliable. Not really, almost reliable. Okay? So what we do is we say something very simple. If it's 100 milliseconds elapsed, you don't need it anyway. Forget that. So keep it for 100 milliseconds in each of the guys in the middle. If you think that you missed it, ask for it once and that's it. If you were asked about it, give it and forget it. You'll never be asked again. After 100 milliseconds, just drop it. You don't need it. By the time comes, just deliver what you have. Okay? That kind of protocol is very simple, has no ACKs, has no duplicates, and has no blocking. What does it do to your loss rate? If you had a probability of loss of P, the more or less you will get 2 times P squared. So if you had 10% loss to begin with, you will end up with 2% loss. If you have 1% loss, you'll end up with 0.02% loss, which is 200 per minute. Remember that now. Okay, that's 1% loss. Okay, so then recovery works for ropes shorter than 30 milliseconds, but that's okay. We made them every 10 milliseconds. So you have a scheme. This is the result. I'm a short guy, so I won't be able to show you. I'll just show you. These 2 lines is what we had before. This is what you have with this scheme. So for the bad 5%, whatever you could do with 0.5%, now you can do with 5% loss. So you are order of magnitude better. Period. By just putting a few nodes in the middle. So now there's also the question of how you do the routing and all of that. We came with some schemes to do it. I'm not going to waste time on it, but just to say that it's not clear if you want to get from A to E and you make a phone call, and A to D is 10 milliseconds and 2% loss, and A to D through C is 20 milliseconds, 1% loss, which one of them do you use? It's not clear. It depends what D to E is. So you need a scheme to decide how routing will happen. So we came up with that based on expected latency, and turns out that it works pretty good. So you have an approach where you localize the real-time recovery of the hop, just based on that protocol, and then you do it the routing as we talked about, and you have a complete system. So we're there at 2006. DARPA is completely out of computer science research, and we're dead in the water. You'll never convince a peer of your, what do you say, a jury of your peer. You'll never convince them at the NSF, because it doesn't work like this. It's never going to work. So then you're out of funding. So I have my third wave, Nilo and Raluca, take this thing, take these ideas, put them into those wireless routers, the Lynxes, the Merakis, and then create wireless mesh networks. More or less with the same scheme, take it one step further. Get great fame in academia, publish papers, put open source, great, but it's not my passion. I want to do the globe. I just want to take care of the campus wireless network. Hopkins can say, connect that, connect each one of them. So then we were dead in the water for 2 years, up until another email arrives, and say, so I go to meet 2 guys, and they say, we think the time has come for the internet to be the infrastructure for TV. There is that TV infrastructure. Media companies, they use satellite, they use private networks for live TV distribution and contribution. Transports, interviews, get it to teleports, put it up to satellite, all of these things. Live programming, can we replace it? That's the question. Okay, do some calculations. I don't know. It's not clear we can do it today. Probably we couldn't do it 5 to 10 years ago. Probably we will be able to do it 5 to 10 years from now. I don't know if we can do it now. These guys came up and said, okay, you know what, let's build it and see if we can do it. So we built a network, basically a test network, And that's the story behind Lifetime Net. And the idea here really is to build a cloud. Okay, we didn't call it like that. We actually I never liked that word. But the customers forced to call it that. What is the cloud? Really, it's a big distributed system. Large-scale distributed system. Just a fuzzy word to say large-scale distributed system. So what the Lifetime Net Cloud does, it can put those overlays, decides as a service provider, so it takes a service provider point of view, put those overlays where you want them, connect them with many internet ISP connections in each place, and you're there. You can be absolutely reliable, you can be absolutely timely. And then what we do at Lifetime Net, we take TV channels anywhere in the world, and we drop them however many places you want, anywhere in the world, within 200 to 300 milliseconds. And the kind of reliability we talk about, you'll see in a second. So I decided to show you that. People here at Hopkins helped me get a regular internet connection to this machine, and I brought a machine that actually is authorized to do it. I decided to focus on one of the overlays. So the cloud has many overlays on it. Each of them runs many TV channels on it, if that's what you want to TV channel. And I decided to focus on one of them because I really like it. It's a channel coming from Atlanta, and we drop it within 200 milliseconds or so in Japan, in Korea, and in London. And let's drop it here at Hopkins. So if we drop it at Hopkins, it will look like that. This machine over here will be this guy, okay? Now let's see if we have luck. Let's hope they are not in So this CNN is the real thing. You probably recognize it. And you're about 4 seconds ahead of everybody else. So if we're seeing it, it's about 4 seconds ahead of if you open your TV. And that's the real thing. Some of that is about 6 megabits per second. You get the message. These guys wanted to do 10,000 of them. We're talking about very, very large scale operation. But not so much. If you calculate and take into account that the satellite, one satellite costs 300 million, and this thing that we're just now doing just like that cannot be done with one satellite. Can't be done. Why? Because we have in London, we have in the US, and we have in the Far East. You can't cover it. You need at least 2 satellites to cover that. Okay? And the speed here, you cannot do through satellite. Because you need to go 30,000 kilometers up and down. Speed of light won't help you with that. Okay, questions? I want to show you another demonstration just to present how fast, just give you an idea of how fast it is, because really it answers the question. Yes?
So what resolution is that downloading?
This is what you get at home, because you get it at home after it comes on my system. Okay, so this is the real thing. I mean, you don't, but the guys in Korea. See? So this is the real thing. This is what, we're not doing internet TV here. This is the real infrastructure of TV. I'm going to show you one that you actually do get through my system. So this channel that I'm going to show now, because I cannot do this game that I'm going to do now with CNN because it's encrypted. I cannot play games with what I want to do now. So this channel that I'm going to show now, you can get it off the air.